Welcome to the polyester family lecture. This will be a two-part lecture because this is kind of a long PowerPoint. This is the first half of those two lectures. When it comes to the thermoplastic polyesters, there are three main members. There is polyethylene terephthalate, there's polybutylene terephthalate, and there's polyethylene naphthalate. We will also talk about a few of the bio-based polyesters, and some other polyesters that you may have heard of are also the unsaturated polyesters, but those are thermosetting. So these are the ones we're concerned with when it comes to the thermoplastic polyesters for industrial applications. Polyethylene terephthalate is a quasi-commodity thermoplastic. It was first produced in 1953 in the UK by Winfield and Dixon. In the US, it was first produced by DuPont in 1977. The current production method for PET is known as a direct polycondensation reaction between terephthalic acid, ethylene glycol, and produces water as a byproduct. This is probably the first of the condensation polymers that we're going to talk about, and so the polymerization process gets a little more complicated from this point forward. PET production is a two-step process. It is produced from ethylene glycol and either dimethyl terephthalate, DMT, or terephthalic acid, TPA. Before the 1960s, the DMT method was preferred. That's a transesterification reaction. But now, Amoco produces very high purity terephthalic acid, and so the direct polycondensation method is preferred. In each case, you're forming a PrePolymer, and that PrePolymer is bis-hydroxyethyl terephthalate, or BIS-HET. So, whether you are making the dimethyl terephthalate or terephthalic acid, you are using AABB type monomers. So you're using either ethylene glycol, or terephthalic acid, or dimethyl terephthalate. So when you're reacting ethylene glycol with terephthalic acid, that is the direct polycondensation reaction. And when you're reacting ethylene glycol with dimethyl terephthalate, that is a transesterification reaction. Whether it is the preferred method, which is the terephthalic acid method, or dimethyl terephthalate is a condensation polymer. So in this case, your dialcohol is your ethylene glycol, and this is your AA monomer. Your diacid, if we're talking about the direct polycondensation, is the terephthalic acid or the dimethyl ester, which is dimethyl terephthalate for the transesterification reaction. So in either case, these are your BB monomer. The OH group reacts either with the acid, or the OH group reacts either with the dimethyl ester. So this is your AA monomer in each case. Depending on which type we're doing, your BB monomer, commercially speaking, is usually a diacid, but in the past it has been this dimethyl ester, your BB monomer. In order to prepare your PrePolymer, you can either start with TPA or DMT, but you make a PrePolymer first, and you make this PrePolymer bis-hydroxyethyl terephthalate, BIS-HET. So this is the structure of the PrePolymer that you're making. So you're taking the TPA and ethylene glycol and reacting them to form this PrePolymer. In this case, the small molecule byproduct is water. Now, in chemical reactions, usually you see just one arrow, but here you see two. What this means is you either have to push the reaction or you have to pull the reaction, because this reaction can go back and forth. The way this is usually done is you pull the reaction. In other words, you remove the small molecule byproduct, usually by vacuum or distillation, so that you take the reactants and push them as far as you can to product, so they don't back react to the starting materials. So in this case, once again, TPA reacts with ethylene glycol to form your PrePolymer. If you're doing this, the transesterification reaction, you have your DMT. This reacts with your ethylene glycol, again, similarly in a equilibrium reaction, to produce methanol. So this is the same concept. We pull off the methanol as best we can, and this pushes the reaction to primarily PrePolymer product that we want. Now, the reaction to produce the small molecule byproduct of water is the commercially relevant reaction. This reaction is no longer done. Even though water is much more difficult to remove than methanol, you have a much more high purity starting material in TPA now, as opposed to the DMT. So the purity of this starting material makes up for the extra energy you have to input to remove the water. Methanol boils at a lower temperature, but you get a lower quality product if you do it by this method. So once again, the commercially viable method is the direct polycondensation reaction, not the transesterification reaction. The prepolymer is then heated at low pressure in the presence of a catalyst to create your polyethylene terephthalate. So this is reacted at 260 degrees Celsius under low pressure in the presence of a catalyst. Again, this is an equilibrium reaction. So you have to push this reaction to completion. What you end up getting is this PET repeat unit. So once again, this is a polymer, polyethylene terephthalate, because it has brackets and an N. And the small molecule that is produced under this reaction is ethylene glycol. Because this is also a starting material, it is collected and then is recycled back to make more of the prepolymer. So the overall commercial reaction scheme that I'm going to be asking you about, in other words, what is the commercial reaction scheme? Does it use terephthalic acid or does it use DMT? Terephthalic acid is the current commercial polymerization scheme. So you take ethylene glycol and terephthalic acid to produce a prepolymer and water. Water is then removed. The prepolymer is then heated in the presence of a catalyst to produce polyethylene terephthalate polymer and ethylene glycol, which is recycled back to make more prepolymer. PET properties. PET has a TG that's 69 degrees Celsius, and it has a melting temperature, which means it is a semi-crystalline polymer. Typical commercial PET resin melts at about 250 degrees Celsius. Now, PET is one of those things where you can use the TG to your advantage. This is a semi-crystalline polymer, but most beverage bottles are clear PET. I said semi-crystalline polymers are opaque or translucent. This is why paying attention to the use temperature versus the glass transition temperature is important. 69 degrees Celsius is above room temperature, and typically the use temperature of a PET bottle is room temperature or lower. They're refrigerated. So if you blow mold a PET bottle and you quench it, you freeze out the ability for that material to crystallize, and it'll be below its TG in its use temperature, so it won't have enough degrees of freedom to crystallize while it's in use. So it will remain clear and advantageous for a beverage bottle. You can create fibers out of it because it has the ability to be semi-crystalline, so you can orient it and you can create something that's crystalline and appropriate for making fibers. So if you have something that is a polyester blend, you're talking about PET. It's the same polymer that you're using for your beverage bottles, it's just in fiber form as opposed to, say, beverage bottle form. And it is in its crystalline state. The fact that this has the ability to be semi-crystalline gives those fibers good tensile strength, which is advantageous for textiles. In the fiber grade, you have an intrinsic viscosity of 0.5 to 0.65, and this is made in a melt-stirred reactor. You also make barrier resins from PET. You can have biaxially oriented bottles. Your intrinsic viscosity for that is generally higher, and if in the injection molded preforms, or a little bit lower than 1.04 for the extruded preforms. You can also make these into heavy-duty reactors and solid-state reactors as well. But the primary application for these is blow-molded beverage bottles. PET does have the ability to have high crystallinity, but when you are producing PET, you can produce films with very good clarity. PET does have low moisture absorptivity, but because it is a polyester and has a bunch of oxygens in it, it does require drying under a nitrogen blanket. So 3 to 4 hours after drying, you pick up about 0.005% moisture. So moisture in the presence of a resin can often act as a plasticizer, and so if you don't remove moisture in resins that can take moisture up, you get poorer mechanical properties or poorer aesthetic appearance. So if something needs to be dried, it should be dried. If PET is drawn, it has good barrier properties. So it has low water vapor transmission and low carbon dioxide transmission. That's why it's used for beverage bottles. If you carbonate a beverage, you want the CO2 to stay in the bottle, and so it can stay fizzy. And anyone who has dropped a beverage bottle and then had the misfortune to open it up, the fizz stays in. until you open it. PET has very good dimensional stability. It has generally low mold shrinkage. It has good chemical resistance. However, it can be attacked by concentrated sulfuric acid or nitric acid. It is soluble in fluorinated and chlorinated acetic acid, phenols, and anhydrous hydrofluoric acid. Now, do not hang out with anhydrous hydrofluoric acid if you don't have to. This is probably the nastiest acid on the planet in terms of corrosivity. But in general, most of the chemicals that PET you're going to come in contact with, it has resistance to. It has very good electrical insulating properties as well. PET has its major area in fiber and films. It is used for slot liners for motors, distributor caps, slot liners for magnetic tape, X-ray and photographic film. It is very widely used in food packaging for boil and bag type pouches. In other words, something that is going to be subjected to elevated temperature. It's also used in pharmaceutical and cosmetic packaging. However, its largest application area is blow molded bottles, and specifically carbonated beverage containers. This is mostly for soda because of its very low gas permeability and its excellent moisture and gas barrier properties. It's also used for bottles for fruit juices. However, this is mainly in Europe. In the US, fruit juice concentrates are generally with K resin, and K resin is considered the biggest competitor of PET in the US. Typically, if you're using a PET fiber, it is designed to simulate wool, rayon, and cotton. If it's a fiber, it has an aspect ratio of greater than 100. In other words, it's at least 100 times longer than it is wide. So aspect ratio is length divided by diameter. For films, you're looking something at a thickness of less than 0.1 inch. PET can be processed by most methods of thermoplastic processing. Extrusion, injection molding. The issue with injection molding is it does have a high TG, and it means you have to put a lot more energy in it to get it to flow. It also has a slow crystallization rate on injection and cooling, so it can take a long time to cool, or you have to have a lot of hold time for injection molding. It, of course, is widely used in blow molding. It's used in casting. It does require drying, so again, 120 degrees Celsius in an inert atmosphere, typically a nitrogen blanket, and it absorbs moisture from the air. So you want the moisture to be less than 0.005. You can accomplish that if you're drying for about 4 hours, but you need to use it right away. Because it's hygroscopic and absorbs moisture from the air, after about 10 minutes, all of that drying that you did is starting to be undone. In about 15 minutes, you have double the amount of moisture that's appropriate. So you want to dry it and use it immediately. So this is my little stop sign, and then this is where I'm going to stop the video number 1 for polyesters, and we will pick this up again in the second video for polyesters.